Our exploration of gravitational waves must start with the concept of black holes. This notion first took shape more than 200 years ago, when Jean Michel and Pierre-Simon Laplace considered a fundamental question. They wondered what would happen if you applied Newton's laws to a scenario where you continually increase the escape velocity, the specific speed an object like a ball or a stone needs to permanently overcome the gravitational pull of a celestial body, such as our own planet. You can determine this velocity with a simple equation. V equals the square root of 2 times g times m divided by r. In this formula, v represents the escape velocity. M stands for the mass of the body you're trying to leave. R is its radius, and g is Newton's universal gravitational constant. This equation originates from setting the object's kinetic energy equal to its potential energy. Looking at this equation, you can see that if you either boost an object's mass without changing its size, or shrink the object while its mass stays the same, the required escape velocity climbs higher. Ultimately, this value can be pushed all the way to the speed of light. This led Michel and Laplace to a straightforward but revolutionary conclusion, that you could theoretically form an object so incredibly massive or so densely compressed that its escape velocity would match the speed of light itself. Today's conception of black holes, which represents a kind of rebirth of the idea, developed from the principles of general relativity. Within this framework, the situation is viewed differently, and it becomes essential to understand that general relativity describes gravity as a geometric phenomenon. For an accessible overview of gravitational theories, you can turn to the book Gravity by Alexander Petrov, which was released by the publisher Vec 2 in 2014. According to this theory, any object with substantial mass actually warps the fabric of spacetime in its vicinity. This warping of space is frequently explained with a common analogy, asking you to picture a flexible surface like a stretched rubber sheet. If you set objects of different weights onto this sheet, you'll see that the heavier ones cause it to sag more deeply, forming a noticeable divot. Smaller objects nearby will naturally roll down into this curve, a visualization that serves as a helpful, if simplified, model of how gravity functions, with celestial bodies pulling on one another by bending the space that surrounds them. Now, let's take this analogy a step further by imagining you place an exceptionally heavy and compact object onto the sheet, keeping in mind that both its mass and its radius are crucial. An object that is large but not very dense will produce a broad, shallow indentation with gentle slopes, indicating a relatively minor distortion of the surface. In contrast, a small but incredibly dense object will form a profound and sharply angled well in the fabric. This is where the surface becomes so severely warped that it creates a zone from which escape is impossible, serving as a parallel to a black hole as described by general relativity. To someone watching from the outside, this appears almost like a hole in the sheet with a distinct border. You are able to fall in, but you can never get back out. And, just as with an actual black hole, when other objects are captured by this hole, its size increases. The mathematics of general relativity does permit some unusual outcomes for the fate of particles that pass beyond the event horizon, with a few theoretical models suggesting the horizon might not even materialize, allowing specific particles to sidestep the central singularity. Yet, in the absence of any special assumptions, the standard prediction is that all matter must inevitably collapse right into the core. At that central point, numerous physical parameters theoretically stretch to infinity, which signals that our known laws of physics no longer apply in that space. and this is a significant dilemma. This raises the fundamental question of whether black holes truly exist. On one side of the argument, their existence is a direct prediction of general relativity, which stands as our current accepted theory of gravity. On the other side, scientists recognize that this theory is not the ultimate description of reality. While it possesses numerous powerful features, its scope is finite, and black holes serve as a prime illustration of the boundaries that nature places on our understanding. What is required is a more sophisticated theory that can accommodate general relativity as one of its fundamental parts. Although theoretical physicists are actively pursuing this goal, theoretical work by itself is insufficient. We also require direct observations of events occurring within incredibly intense gravitational fields. Being able to observe black holes would be a tremendous help, but this poses a challenge. How do you spot an object that is entirely black and from which nothing, not even light, can break free? The single most direct answer that emerges is a phenomenon known as Hawking radiation. The theory put forward by Stephen Hawking in 1975 postulates that black holes ought to gradually lose mass and dissipate over time. But for black holes the size of stars or the supermassive ones at galactic centers, this evaporative effect is practically insignificant, as they typically gain mass by consuming matter and radiation far faster than they lose it. This process of evaporation would only be relevant today for theoretical primordial black holes, which are thought to have formed in the early cosmos with tiny masses, comparable to an asteroid, and sizes akin to subatomic particles. The mechanism of black hole evaporation is often explained with the following visual. Throughout the vacuum of space, pairs of what we call virtual particles are continuously popping into existence, and then immediately destroying each other. This phenomenon doesn't break any laws of physics, and a useful comparison can be made. Picture yourself as a bank employee who occasionally takes cash from the register, but leaves a note, always repaying the loan the following day. In this scenario, nothing out of the ordinary has occurred, as you simply borrowed the funds for a brief period and then put them back. But now, suppose a situation arises where you are unable to repay the loan. Perhaps a financial crisis hits, and after borrowing the money you find you cannot return it. From the bank's point of view, this amounts to an evaporation of funds. Cash has vanished, although the bank now holds more of your IOUs. Applying this back to black holes, imagine a pair of these virtual particles materializes right at the edge of the event horizon, where one particle is pulled into the black hole, while its partner manages to fly away. To an observer positioned at a safe distance, it would appear that particles are being emitted from the black hole, and the sole available energy source for these particles must be the mass of the black hole itself. While this provides a decent mental picture, it fails to encompass all the crucial details of the Hawking evaporation process. A fundamental requirement in the original theoretical model is that the black hole's event horizon must be dynamic and not remain in a fixed, unchanging state. If you're interested in exploring this subject further, a 2015 brochure by Emily Akhmedova titled The Birth and Death of Black Holes offers a remarkably clear explanation using analogies. This relates to the well-known Casimir effect, which demonstrates that a vacuum isn't empty, but is actually teeming with both virtual particles and electromagnetic waves. When two conducting plates are positioned parallel to one another, they block waves with lengths shorter than the gap between them, resulting in a lower density of these virtual waves inside compared to outside, which in turn generates a force that pulls the plates together. Following that logic, moving the plates apart, causes the emission of waves, transforming virtual waves into real ones, much like the sound produced when you clap your hands. Now, imagine a black hole that has a non-stationary horizon. This horizon acts as a boundary separating space into two distinct regions. You can cross it from the outside, but you can never escape back out. The motion of this horizon can generate a unique effect akin to a one-handed clap, drawing waves and particles out of the vacuum and making them real. This process, however, demands energy, which is siphoned directly from the black hole's mass. The evaporation of a black hole is fundamentally a quantum phenomenon, where the horizon's size plays a critical role. For enormous black holes, the curvature of this horizon is so slight that the effect is nearly imperceptible. To give you a parallel, our distant ancestors living on Earth, with its radius of about 6,400 kilometers, were completely unaware of its curvature. Had the planet been 10 times smaller, its roundness would have been obvious. Unfortunately, the actual observation of black hole evaporation is far beyond our current technological reach. Bringing our focus back to the present state of astrophysics, let's review the kinds of black holes we are familiar with. The first type is stellar mass black holes, which are born when a massive star exhausts its nuclear fuel. After fusing hydrogen into helium, and then helium into heavier elements up to iron, the star's core can no longer sustain fusion and catastrophically collapses. If nothing halts this implosion, a black hole is formed, typically with a mass about 10 times that of our Sun. An object of this size is considered a massive black hole, and its rate of evaporation is incredibly slow. Furthermore, the universe isn't empty. There is always interstellar debris and the pervasive cosmic microwave background radiation. This relic radiation has a current temperature of 2.7 Kelvin, which is actually hotter than these massive black holes. As a result, this radiation constantly falls into them, causing their mass to increase rather than decrease, making any evaporation completely negligible. Next are the supermassive black holes that reside at the centers of galaxies. There are two primary theories for their origin. Either immense clouds of gas collapsed directly to form them, after which they grew by consuming matter, or they began as smaller black holes that merged and then expanded through accretion. Regardless of their formation, these cosmic giants evaporate even more slowly than their stellar mass counterparts, because a black hole's temperature is inversely proportional to its mass, rendering their evaporation impossible for us to observe. Given these challenges, you might wonder how certain astrophysicists are about the existence of black holes at all. Here's a practical measure. No one has yet been awarded a Nobel Prize for their discovery, as definitive confirmation remains elusive. However, despite the lack of absolute proof, nearly every astronomer would confidently bet that black holes are real. It's crucial to understand that we might not be talking about the specific black holes described by general relativity, but a wider category of collapsed objects, entities lacking a solid surface and not governed by any standard equation of state. We don't witness events that are exclusive to black holes because our observations are limited to what occurs in their immediate surroundings. Therefore, we should technically refer to them as black hole candidates, since we can only analyze the behavior of matter caught in their gravitational pull, such as the radiation from their accretion disks. The most renowned and widely cited paper on this subject from my country was published in 1973 by Nikolai Shakura and Rashid Sunyaev, who developed a foundational model for the flow of matter around black holes, a work that became a cornerstone of astrophysics for many years. Nevertheless, Studying accretion disks or tracking the orbits of stars around supermassive black holes doesn't provide conclusive proof that these objects possess an event horizon instead of a surface. It's possible that in the near future, our primary source of information about black holes will come from gravitational waves, which are essentially ripples in the fabric of space-time. We use a geometric theory to describe gravity, and a common analogy to visualize its effects is an elastic surface, like a rubber sheet. Imagine you are a godlike being, and you poke this rubber sheet with your finger, sending a ripple across it. That ripple is conceptually similar to a gravitational wave, though in this analogy, the push comes from an external source. In reality, any disturbance must originate from objects existing within the surface itself. While you technically emit gravitational waves just by waving your arms, the effect is extraordinarily weak. A powerful signal requires the movement of massive and, crucially, compact objects. Not just heavy, but dense enough to significantly warp spacetime in a concentrated area. For a strong emission, you also need asymmetry, as a stationary object radiates nothing. Fortunately, nature provides us with the perfect asymmetric processes. For instance, consider a scenario where two massive stars go supernova, each leaving behind a black hole. These two black holes can then become gravitationally bound, orbiting a common center. Picture two heavy balls rolling on our elastic surface. As they circle each other, they will inevitably generate ripples, which are the gravitational waves. As these orbiting black holes emit gravitational waves, they carry away both energy and angular momentum from the system. This loss causes the black holes to gradually spiral closer to one another. Due to the nature of gravity, as energy is removed from a two-body system, the objects pull nearer and their orbital velocity actually increases, eventually accelerating to approach the speed of light. Just prior to their collision, each black hole carries a tremendous amount of kinetic energy. Imagine an extreme scenario where you could hurl one black hole directly into another, creating a collision at the fastest speed imaginable, the speed of light. You might wonder how the resulting immense energy is released, given that black holes lack a physical surface. Instead of two solid objects clashing, we are witnessing the merger of two space-time regions defined by their horizons, which unleashes this colossal energy entirely as gravitational waves. When two black holes merge, they produce an incredibly powerful burst of gravitational waves, a signal that we anticipate gravitational wave antennas will capture very soon. This event represents our most promising method for finding black holes, and its detection would accomplish two monumental scientific objectives at once. Primarily, it would provide the first direct confirmation of gravitational waves, moving beyond the indirect evidence we currently possess. Our current evidence comes from observing a binary system of two neutron stars, not black holes, where one acts as a pulsar, a celestial object emitting regular pulses that function like an exceptionally accurate clock. Astronomers noticed the two stars are spiraling closer together, a behavior whose only logical explanation is the energy loss due to gravitational waves, perfectly matching the forecasts of general relativity. This groundbreaking discovery and its subsequent study of the binary radio pulsar led to a Nobel Prize in physics, and the findings have since been confirmed by observing dozens of similar systems. The second major achievement would be that by capturing a signal from merging black holes, we would gain powerful evidence for our theories about their fundamental nature, while also directly recording gravitational waves and thus validating the geometric interpretation of gravity. Following the merger, the new, larger black hole's horizon will vibrate for a period, generating its own distinct gravitational wave signal that we might also detect. This is why the entire field of gravitational wave detection is viewed as being incredibly promising. While black hole mergers are monumental, the collision of neutron stars is actually considered the leading candidate for the very first gravitational wave signals you and I might see detected. Although neutron stars are less massive and dense than black holes, we anticipate that facilities such as LIGO and Virgo can capture the signal from a relatively nearby merger within the next few years. As technology improves, we will be able to see even more distant events, eventually reaching out to distances of 200 to 250 megaparsecs. These merging neutron stars are a common outcome in the life cycle of massive binary star systems. From our observations of binary radio pulsars, calculations suggest that a merger like this happens in a galaxy similar to our own roughly once every few tens of thousands of years. In contrast, the merger of two black holes, or a black hole with a neutron star, is a significantly rarer event. The study of these cosmic collisions dates back decades, with pioneering work by figures like John Clark, Douglas Erdley, and Blinikoff. Since the 1980s, scientists have relied on numerical simulations run on the world's most powerful supercomputers. Yet many fundamental questions are still unanswered. A neutron-star merger can be described as a truly golden event. And I mean that quite literally, as current models propose that the vast majority of gold in the cosmos was forged in these exact collisions. These mergers are spectacular, radiating brightly across the entire electromagnetic spectrum. They are not just potent sources of gravitational waves. They also unleash a staggering amount of energy as they combine, heating the matter to unimaginable temperatures. This process generates a powerful stream of neutrinos alongside intense electromagnetic radiation. This makes merging neutron stars the primary suspects for causing short gamma-ray bursts, which are fleeting cosmic explosions lasting only a few seconds. After observing hundreds of these bursts over almost 50 years, all evidence points to this explanation as the best fit. The final piece of the puzzle, the definitive proof, will be to observe a gamma-ray burst and a gravitational wave signal at the same time, an achievement we expect to happen within this decade. In the wake of the merger, new elements, including radioactive ones, are forged. This process triggers a powerful explosion, similar to a supernova, but one that shines most brightly in the infrared part of the spectrum. We call these events kilonovae. The name comes from an early, optimistic estimate that they would be 1,000 times brighter than novae. More recent calculations show they are closer to 100 times brighter, leading some astronomers to humorously suggest the name hectanovae, but the glow from the explosion itself lasts for an extended period. Observing these kilonova flashes in the infrared is crucial for determining the precise location of the merger in the sky. For the foreseeable future, even with more detectors, gravitational wave observations by themselves won't be able to provide highly accurate coordinates. However, when new facilities in India join the 2 American and 1 European detectors, we can triangulate the source much more effectively, allowing us to point our astronomical satellites and largest ground-based telescopes directly at the event. There is also a more speculative possibility. If compact objects contain quark matter, then fragments of it might be flung out after a merger. This exotic substance could potentially exist in tiny, stable bundles called strangelets. We are hopeful that specialized cosmic ray detectors like AMS-02 might one day capture one. The fact that none have been found yet is, in itself, an important negative result, giving us significant new information by suggesting that quark matter might not exist in this form. So, this brings us to the crucial question. What methods do scientists actually use to detect these elusive gravitational waves? A gravitational wave distorts any object it travels through by alternately compressing and stretching it. If you have a collection of objects, you can see this effect by monitoring the changing distances between them. Imagine, for instance, a ring of beads you've placed in space. A passing gravitational wave would rhythmically warp this perfect circle into an ellipse and back again, with the exact orientation determined by the wave's polarization. You would witness this as a continuous cycle of expansion along one axis and contraction along another. The ability to precisely measure these shifts between the beads would allow you to detect the faint gravitational wave responsible for the vibrations. In the early days, researchers tried a different approach, using massive metal cylinders, such as those made of aluminum, to see how they would be squeezed and stretched. These pioneering experiments, initiated by Weber in the late 1960s, went on for many years. However, this kind of detector has a major drawback. It's only sensitive to a very limited frequency range that matches the cylinder's own resonance. A significant problem since cosmic sources are unlikely to emit waves at that exact frequency. Consider that the signal produced by two merging neutron stars, for example, sweeps across a range of frequencies as their orbital period shortens. Resonant mass detectors simply lack the required sensitivity. For them to register anything, an incredibly powerful burst of gravitational waves from a close event is needed, like two neutron stars colliding in a neighboring galaxy, or an asymmetrical supernova explosion nearby. Although Weber asserted he had recorded a signal from supernova 1987A in the Large Magellanic Cloud, the scientific community largely dismissed his finding. Even more advanced, cryogenically cooled facilities like Allegro in the United States and Nautilus and Auriga in Italy failed to produce any meaningful detections. Consequently, a completely different method is employed today. The primary effort now centers on massive instruments known as laser interferometers, whose design specifications were tailored to the anticipated characteristics of a signal from merging neutron stars. These facilities bear a strong resemblance to the historic apparatus that Albert Michelson and Henry Morley used to disprove the existence of the ether, though contemporary versions are vastly larger. Picture a set of mirrors suspended kilometers from each other inside a long vacuum tunnel. Even the slightest displacement of these mirrors relative to one another can be registered. A laser beam is directed back and forth between the mirrors, and following numerous reflections, it arrives at a sensor that monitors its interference pattern. Any movement of the mirrors causes a change in the laser's travel distance, which in turn modifies that interference pattern. This technique offers an exceptionally precise way to measure minute changes. Naturally, the mirrors are never perfectly still. They are sensitive enough to pick up vibrations from heavy trucks driving many kilometers from the observatory, and even quiver due to their own internal temperature, a phenomenon known as thermal fluctuation. The very photons of the laser can exert enough pressure to make the mirrors vibrate. While these are the kinds of subtle disturbances we're dealing with, every one of them can be calculated and eliminated from the data. In fact, the team under Vladimir Braginsky at Moscow State University's physics department pioneered many of the techniques used to counteract these interferences. Just think about the scale of this endeavor. Researchers are trying to spot a length variation in an interferometer arm that spans several kilometers, a change as small as 10 to the power of minus 21 meters. This distance is profoundly smaller than an individual atom, and tinier still than an atomic nucleus. Astonishingly, it is a measurable quantity. It won't be long before gravitational waves are detected, which will not only give us a new way to observe the cosmos, but also offer solid proof for the existence of black holes. Following that breakthrough, the focus will shift to a cosmic version of our bead experiment. For many years, a space-based laser interferometer has been in the works, a project where the separation between the laser instruments will be measured in the tens of millions of kilometers. This initiative, now known as LISA and managed by the European Space Agency, is scheduled for launch in 2034. An instrument of this scale will be capable of detecting waves generated by supermassive black holes, which are immense objects, roughly the size of an astronomical unit. Consequently, the detector itself needs to be enormous, because a binary system of supermassive black holes in a far-off galaxy radiates gravitational waves whose wavelengths are similar to the separation between the black holes themselves. Future generations of even more sophisticated space-based detectors might even succeed in capturing primordial gravitational waves from the very beginning of the universe. Engineered gravitational wave observatories face an intriguing form of competition from natural cosmic phenomena: radio pulsars. We know the rotation periods of these celestial objects with an incredible degree of accuracy, on par with the finest atomic clocks we have on our planet. This precision allows us to forecast the arrival of their next pulse down to the fraction of a second, provided nothing gets in the way. Since a gravitational wave warps spacetime itself, a pulsar's signal traversing such a wave will be slightly delayed, an effect that we can measure. This concept was originally proposed by Mikhail Sajin back in 1978. The cosmos is permeated with a background of low-frequency gravitational waves, a result of countless binary stars, orbiting pairs of supermassive black holes, and their eventual mergers throughout distant galaxies. By monitoring a few dozen millisecond pulsars, it's possible to identify correlated shifts in their pulse arrival times, which are caused by this gravitational wave background. At present, 3 large-scale projects are pooling their resources, serving as our primary tool for studying these low-frequency waves until the era of giant space-based interferometers begins. So-called runaway stars generally move at speeds between 10 and 30 kilometers per second compared to the stars around them. Stars also have an orbital velocity around the galactic center. Our Sun, for instance, travels at a little over 200 kilometers per second. But when we characterize an object's individual motion, its speed relative to its local stellar neighborhood, or the surrounding interstellar gas, is the crucial parameter. It's worth noting that, on average, both neutron stars and black holes travel at significantly greater velocities. Objects in space can gain speed through a few different processes, with the most direct method being gravitational interaction with other bodies. An object can effectively borrow energy from another, which increases its own velocity. This exchange becomes considerably more efficient when more than 2 bodies are involved, potentially leading to a dramatic acceleration of one of the objects. A recently discovered class of sources known as hypervelocity stars serves as a perfect example of this. These stars travel at speeds that are immense by stellar standards, sometimes reaching 1,000 kilometers per second. Such incredible velocity is a clear indicator of an encounter with something exceptionally massive. And within our galaxy, the only candidate is the supermassive black hole at its center, which has a mass of about 4 million suns. The most common theory for their creation suggests that if a pair of stars orbiting each other passes very close to this black hole, the system can be ripped apart by tidal forces. In the ensuing gravitational tug-of-war, one of the stars can be catapulted away at an extremely high speed, achieving escape velocity from the galaxy itself. This ejected object could be an ordinary star, a neutron star, a black hole, or a white dwarf. We are now aware of dozens of these hypervelocity stars, all of which are at great distances from us. Observations confirm that they are indeed flying outward from the center of the galaxy. So far, all identified objects are typical, relatively low-mass stars, as we have not yet discovered any hypervelocity neutron stars or black holes created through this process. There is, however, a more exotic mechanism that can create a hypervelocity object, which you might summarize with the phrase, "What doesn't tear us apart makes us faster." If a single star survives an encounter with the supermassive black hole, having only been stripped of some of its material by tidal forces, it can still receive a significant speed boost. This allows it to become a hypervelocity star in a rather unusual way, escaping au naturel, so to speak, though compact objects cannot be accelerated like this. Shifting our focus to ordinary stars, you'll find an intriguing category of objects known as runaway stars. As their name suggests, they travel at higher speeds than their neighbors, often 70 or sometimes even 100 kilometers per second. The question is, how do they acquire this speed? It turns out there are two main pathways. The first method is one we've already touched upon, acquiring additional energy through gravitational interaction. In this case, however, the interaction isn't with a supermassive black hole, but occurs through collective dynamics within a dense young stellar association, where some stars gain energy and are ejected, while others lose it. The second method involves binary systems in which one of the two stars explodes as a supernova. When one star in a binary pair suddenly becomes lighter due to a supernova explosion, its companion is no longer gravitationally bound to it. The surviving star then flies off, largely retaining the orbital velocity it had just before the system was disrupted. For example, if its speed in orbit was 100 kilometers per second, it might escape at a velocity of 70 kilometers per second after the breakup. This process is also a natural way for neutron stars and black holes to acquire high speeds, since their very formation is the result of such an explosion. Think of a stone being released from a sling. It was spun around rapidly and then let go. In much the same way, a star or black hole is held in orbit by gravity, and when that gravitational pull suddenly weakens, the object is flung into space. This mechanism can accelerate objects to impressive speeds of hundreds of kilometers per second, especially neutron stars and black holes, because they can exist in very close binary systems. The reason compact objects can achieve higher speeds is straightforward. You cannot bring two large, ordinary stars very close together, as their own radii are several million kilometers, and they grow even larger as they evolve. But if one of the stars has already become a black hole or neutron star, the pair can orbit each other much more tightly. A closer orbit means a faster orbital speed. So when the second star explodes, the compact object can be ejected at an incredibly high velocity. In fact, it is theoretically possible for the system to become so tight before the breakup that this process could launch a compact object at a speed exceeding 1,000 kilometers per second. Finally, there are also specialized acceleration mechanisms devised to explain specific observational data that are available only to neutron stars and black holes. So, where does the need to explain this come from? We have the ability to measure the speeds of compact objects in various situations, though the techniques differ slightly. For instance, by observing a radio pulsar over several years, we can accurately measure its coordinates and notice that it is shifting its position in the sky. If we know the distance to that pulsar, we can then calculate its speed, or more precisely, the projection of its speed across the celestial sphere. Using techniques like this, the speeds of hundreds of pulsars are now known. We can also observe this displacement in other objects, like stars that are X-ray sources or are visible in optical light, allowing us to determine their motion projected onto the sky. In certain instances, we can also observe the consequences of a fast-moving pulsar's interaction with the interstellar medium, which forms a shock wave and a beautiful nebula around it. This interaction sometimes allows us to estimate the object's speed based on how far the neutron star has traveled from the center of the supernova remnant that produced it, provided we know when the explosion happened. For most supernova remnants, we can obtain a fairly reliable age estimate. All of this data allows us to statistically determine the speeds of young radio pulsars, which primarily form in the plane of the galaxy's disk. Initial observations during the 1970s revealed that pulsars travel at velocities several times greater than the massive stars from which they originate, implying they undergo some form of rapid acceleration. By the 1990s, it became evident that these pulsars move even faster, a realization that stemmed from more precise methods for determining their distance from us. Previously, these distances were underestimated by an average factor of 2, largely because our understanding of density distribution within the galaxy was incomplete. When a radio signal journeys through the interstellar medium, it disperses because electromagnetic waves of varying frequencies move at different speeds. This environment is not a perfect vacuum. As a result, these waves arrive at our instruments at slightly different moments, which can stretch the peak of a pulse by a factor of 100 if you are observing across a broad frequency range. By analyzing the signal's travel distance and the number of electrons it encountered, we can calculate this value. But until the mid-1990s, our measurements were imprecise, causing us to misjudge pulsar speeds by about a factor of 10. This means their average velocities were actually 10 times higher than those of their progenitor stars, a discovery that posed a significant challenge. Since this is an exceedingly common phenomenon, you cannot attribute all of these high speeds simply to the breakup of binary star systems, especially as some neutron stars are born from solitary stars or in very distant binary pairs. This points to a unique acceleration mechanism that applies specifically to neutron stars and, as it was later discovered, to black holes as well. The fundamental connection between a supernova explosion and the velocity it imparts to the remnant object was understood long before the 1990s, when the problem grew even more urgent. In 1970, Iosif Shklovsky was among the first to formally consider the acceleration of pulsars, identifying asymmetry as the key. Interestingly, Leonid Ozernoy had explored the concept of asymmetrical explosions even earlier, in 1964. But his work was focused on gravitational waves, not the motion of neutron stars. A neutron star is forged in the heart of a supernova, an event that unleashes a staggering amount of energy in just fractions of a second, primarily through a massive flux of neutrinos. The total energy radiated is comparable to what our sun will produce over its entire existence. Having such a vast energy reserve is incredibly useful for our problem, as our goal is to give a compact object a significant amount of additional kinetic energy. I can offer an analogy. If you have an enormous budget, even a very small percentage of it can represent a substantial sum of money. For many years, roughly 1% of the budget for major American space missions was allocated to public outreach, which is how the world received such beautiful astronomical images and videos. Even though NASA now centralizes its outreach funding, it continues to deliver stunning visuals. If a mission costs $1 billion, 1% of that is $10 million, a considerable figure for science communication. In the same way, if the immense energy of a supernova is released asymmetrically, with even just 1% more power in one direction, the compact object that forms will feel an unbalanced force. In accordance with the law of conservation of momentum, this asymmetry would cause the newborn compact object to be propelled in the opposite direction, potentially reaching speeds of several thousand kilometers per second. The critical question, then, is what could possibly create this imbalance? We still lack a definitive answer, and the debate continues, partly due to a scarcity of observational data and the extreme complexity of supernova physics. There are two primary models that attempt to explain this asymmetry. The first proposes that the explosion itself is inherently lopsided, creating a situation where the newly formed compact object is surrounded by ejected material that can push it and accelerate it unevenly. The second major idea, which was first discussed in detail by Nikolai Chugai in 1984, revolves around the neutrinos that carry away the vast majority of the energy from the explosion. Neutrinos are generated in colossal numbers within the star's collapsing core, through a process known as neutronization, where electrons are captured by protons. If the core's material doesn't immediately vanish behind the event horizon of a black hole, there comes a moment when it becomes transparent to these neutrinos, allowing them to stream outwards. The main challenge is to devise a way for this neutrino flood to be asymmetrical. One proposal suggests that if the matter distribution is uneven, neutrinos will flow more easily through the less dense regions, creating a net propulsive force that pushes the neutron star in the opposite direction. A different concept involves the influence of intense magnetic fields, which can guide the motion of neutrinos. In a perfectly symmetric arrangement, like a simple dipolar magnetic field, you would get two identical neutrino jets, resulting in no net thrust. However, if the magnetic field in a very young, turbulent neutron star is asymmetrical, its jet engine would operate unevenly. With less thrust in one direction and more in another, the neutron star would be propelled forward, an idea central to the magnetic explosion model developed by Gennady Biznovachi-Kogan and his colleagues. In this scenario, a break in symmetry can also occur, which provides the necessary thrust to accelerate the compact object. A comparable process can take place with black holes if their formation happens in two stages rather than instantaneously. Should the matter not collapse directly beyond the event horizon, but first create a body akin to a young neutron star, what we call a proto-neutron star, then neutrinos and jets of material can escape outward for as long as this object exists. And if this outflow is asymmetrical, the newborn compact object gains momentum. Once a black hole finally does form, it carries this acquired velocity with it. The speeds for black holes tend to be somewhat lower than for neutron stars, for the simple reason that they are significantly more massive. Whereas a typical neutron star has a mass of about 1.5 times that of our Sun, a standard black hole is around 5 to 10 solar masses, resulting in speeds that are several times slower, which aligns well with what we observe. We have a good deal of data on neutron stars, as there are about 1,000 known radio pulsars, and we have measured the velocities for many of them with high precision. In contrast, Our knowledge of black holes is much more limited. Only a handful of candidates for isolated black holes exist, and their speeds are roughly estimated at around 100 kilometers per second. However, we are aware of approximately 50 binary systems containing black holes, and for these, we can measure the system's velocity. In certain instances, we observe that the entire binary system is moving at an unusually high speed, suggesting an external force has accelerated it. This phenomenon is linked to the extra velocity that black holes gain during their formation. The average speed is, again, several times less than that of neutron stars, which seems to confirm our hypothesis. The acceleration strategy for both neutron stars and black holes is the same, but the less massive objects are easier to propel. With neutron stars, we gain additional insight into the acceleration mechanism by examining the mutual orientation of the spin axis and the direction of motion. Observations reveal that the angle between these vectors is not random. Instead, they show a tendency to be roughly, but not perfectly, aligned. This detail might indicate that the duration of the propulsive mechanism is neither extremely brief nor overly extended when compared to the rotational period of the newly formed neutron star. If the propulsive engine had operated for a very long time on a spinning star, the momentum transfer would have averaged out relative to the axis of rotation, aligning the final velocity with that axis. Conversely, if the acceleration had been nearly instantaneous, the two vectors could have been entirely uncorrelated. Previous theories predicted the angle would be very close to 0 or 90 degrees, but we can now set those particular scenarios aside. There exists another, far more exotic acceleration method specific to black holes, which we call gravitational rockets. Since massive stars often form in pairs, you can have a binary system where both stars are exceptionally large. After they both explode, they can give rise to a pair of black holes. In rare situations, the system remains bound, surviving the first supernova, and then the second, leaving us with a binary black hole. Over vast timescales, such a system becomes progressively more compact, as the two black holes emit gravitational waves while orbiting one another, which carries away both energy and angular momentum. This causes the black holes to spiral ever closer together, until they ultimately merge. It was back in the 1960s that scientists first understood that gravitational waves emitted by an asymmetrical binary system would not be uniform in all directions. As the two objects circle each other in a tightening spiral, a relativistic effect comes into play. Any object moving at high speed appears to emit more radiation in its direction of motion. Because achieving perfectly equal masses is virtually impossible, the gravitational wave emission becomes lopsided, a phenomenon that is especially pronounced during the final moments, as the black holes are essentially plunging into each other. Consequently, these waves carry away not just angular momentum, but also linear momentum. A truly remarkable thing then happens. You start with a pair of black holes whose center of mass is stationary relative to you. But as they draw nearer, the entire system begins to pick up speed, and after they combine, the single resulting black hole hurtles away at an immense velocity. This process is aptly named a gravitational wave rocket, and its elegance lies in the fact that the final speed depends only on the ratio of the masses, not their absolute values. This means that, whether you merge two black holes of 10 solar masses each, or two supermassive black holes of 5 and 10 billion solar masses, the resulting object can achieve the same final velocity. Calculating this speed with precision is incredibly challenging because the final stage involves tremendously strong, rapidly changing gravitational fields. problems that even our most powerful supercomputers struggle to solve. Nevertheless, we can estimate the order of magnitude of these speeds, which turn out to be in the hundreds of kilometers per second, with maximums potentially exceeding 1,000 kilometers per second. To give you a sense of this incredible velocity, it is fast enough for an object to escape the gravitational pull of our entire galaxy. To leave Earth and become an orbiting satellite, you need the first cosmic velocity, which is almost 8 kilometers per second. To break free from Earth's gravity entirely and journey into interplanetary space requires exceeding 11 kilometers per second. There is an even greater speed needed to leave the solar system, and a greater one still to escape the galaxy. While it depends on your starting point, from some regions, 1,000 kilometers per second is sufficient to become gravitationally unbound from the Milky Way and begin a journey through intergalactic space, a feat that these accelerated black holes can achieve. When two galaxies collide, for instance, a slight possibility exists that their central supermassive black holes will merge, and the newly formed larger black hole will gain enough velocity to be ejected from the new galaxy. This phenomenon was particularly common billions of years ago, during the early stages of galactic formation, when galaxies were less massive and therefore easier for these objects to escape. Today we can observe several galaxies where we suspect black holes, after merging, gained substantial speed. While they couldn't escape the massive galaxy, they are noticeably displaced from the center. Ultimately, this means that both neutron stars and black holes are not confined to our own galaxy, but also populate the vastness of intergalactic space. There are numerous mechanisms that can accelerate these objects to the incredible speeds required to break free from their home stellar islands. As a result, there are billions of these solitary compact objects, neutron stars and black holes, drifting through the cosmos. But what is their precise number? Let's narrow our focus to our own galaxy. The Milky Way is immense, home to approximately 400 billion stars. To put that into perspective, consider that the average human head has fewer than 100,000 hairs, so the scale we're dealing with is truly vast. From here, we can make a rough calculation of how many neutron stars and black holes are present within our galaxy, or more accurately, how many have been created over its entire existence. Neutron stars and black holes are the remnants of supernova explosions, and we can estimate the frequency of these events in our galaxy. Currently, a supernova occurs roughly once every 30 years, which averages out to about 3 events per century. Given that our galaxy is approximately 10 billion years old, and since this is a rough estimate, I'll stick to round numbers, we can perform a simple division. This calculation suggests that throughout the galaxy's history, around 300 million neutron stars and black holes should have come into being. It's very likely, however, that the rate of supernova explosions wasn't always constant. It was probably higher in the distant past, when the galaxy was young and actively forming stars. Furthermore, it's possible for black holes to form without a spectacularly bright explosion. Taking these factors into account, a more reasonable estimate places the total number of neutron stars and black holes at around 1 billion. We can even attempt to separate this figure into individual counts for neutron stars and black holes. The key question is their ratio. We believe neutron stars originate from lighter stars, those with masses between about 8 and 30 times that of our Sun. Black holes, on the other hand, are formed from much more massive objects. Since larger celestial bodies are always less common than smaller ones, there are significantly more neutron stars, perhaps 3 to 4 times more, or even as many as 10 times more. This leads to an estimate of nearly 1 billion neutron stars and over 100 million black holes in our galaxy alone. So the question naturally arises, why don't we see them all? The answer is fairly straightforward. Think about it this way. There are over 6 billion people on Earth, yet on social media you are likely connected to only a few hundred, or at most a few thousand of them. The situation is much the same for the neutron stars and black holes that we have actually identified through observation. For those of you who are interested in looking at the data yourselves, I can point you to the online catalogs that professional astronomers use. The primary resource is the catalog of radio pulsars, which are periodic, solitary neutron stars, hosted on the Australia Telescope National Facility website. Additionally, you can find a catalog of magnetars at McGill University in Canada, and another dedicated to cooling neutron stars. We tend to be connected with our acquaintances, people who aren't necessarily close to us geographically, but are somehow prominent. You might think, then, that we would at least know about most of the neutron stars or black holes in our solar neighborhood, but that isn't the case at all. We are only aware of the most conspicuous ones. Some are visible simply because they are close by, while others are genuine cosmic celebrities, emitting tremendous amounts of energy. It's just like on social networks, where countless people follow the posts of someone like Stephen Fry or another major public figure. They are universally known. The circumstances for neutron stars and black holes are analogous, representing a classic astronomical challenge. We can easily spot the bright and noticeable objects even from great distances, but the ordinary, solitary, compact stars are incredibly difficult to observe. For one, young neutron stars are easier to see because their high activity makes them manifest as radio pulsars, which are fascinating objects. In contrast, solitary stellar mass black holes are almost entirely invisible on their own. They don't flare up or give off any telltale signs. However, there is a very effective method for detecting them. Neutron stars and black holes are exceptionally compact, meaning they pack an immense amount of mass into a tiny volume. From the standpoint of gravity, a neutron star or a black hole creates an incredibly deep gravitational well. If you were to drop something onto one of these objects, it would reach the surface, or the event horizon for a black hole, at a velocity approaching or equaling the speed of light. If a substantial amount of material is drawn in, it will inevitably interact with itself. For example, if you aim a stream of gas, the most common substance in space, at a compact object, friction within the inflowing matter causes the gas streams to lose energy and heat up to millions of degrees. The result is a brilliantly bright source of X-rays that we can detect. So, what kind of matter is available in space to fall onto these objects? To answer that, we need to look again at ordinary stars, as most of them, particularly the massive ones, are born in pairs. Eventually, the inward collapse of a cosmic cloud can be halted entirely by what is known as centrifugal force. To bypass this obstacle, nature has an elegant solution. The cloud splits into two distinct parts. While each new fragment rotates slowly on its own axis, the pair orbits a shared center of mass at high speed, allowing both of them to resume their contraction and ultimately give rise to a binary star system. Should at least one of these stars evolve into a neutron star or a black hole, its companion provides a ready source of material that can be drawn toward the compact object. As a result, a large fraction of the neutron stars and black holes we currently detect exist within these binary systems, where matter flows from the neighboring star onto the compact object in a process called accretion. Yet, compared to the trillions of stars in existence, such pairings are relatively rare for a couple of key reasons. First, not every star is born as part of a binary system. And second, there are several mechanisms that can tear a stellar pair apart. You can picture gravity as a kind of rope connecting two objects as they orbit a common center of mass. Much like Tom Sawyer spinning a dead rat on a string, their rotation creates an outward pull. Of course, if the rat were as heavy as Tom, they would both be flung apart in opposite directions. To snap this gravitational rope, you would need to abruptly decrease the mass of one of the stars. Nature has a perfect method for rapidly shedding stellar mass: a supernova explosion. As you may recall, stars that are 10, 20, or even 30 times more massive than our Sun end their lives in these cataclysmic events. After such a blast, what's left is often a neutron star with a mass of only about 1.5 or 2 solar masses, meaning the vast majority of the original star's matter has been violently ejected. Now, the surviving companion star is attracted not to 30 solar masses, but to a mere 1 or 2. The gravitational bond shatters, and the system dissolves, leaving most neutron stars and black holes as solitary wanderers, with nothing nearby to feed on. This brings us to a critical challenge. How can we possibly spot these old, isolated neutron stars, or, for that matter, lone black holes? While the task might seem fundamentally impossible at first, a closer look reveals it is quite straightforward, even if it remains unsolved. Space is not a perfect vacuum. It is filled with gas and dust. This interstellar medium is, after all, the very substance from which stars, including those that become neutron stars and black holes, are formed through gravitational collapse. Incidentally, if you were to design a starship for interstellar voyages, this medium would present a major engineering challenge. On one hand, you have compelling science fiction concepts about using the hydrogen in space as fuel. On the other hand, you would need to travel near the speed of light to make the journey worthwhile. From your ship's perspective, every hydrogen atom in your path would slam into you at nearly light speed. This would create a host of dangerous effects, ranging from intense heating to the generation of harmful radioactivity, making it a serious technical hurdle for interstellar travel. The definitive discovery of this interstellar gas and dust occurred only in the early 20th century. Its presence becomes obvious as it absorbs light from distant stars, causing them to appear redder. The dark filament-like lanes you see in photographs of many disk galaxies are interstellar dust, while the magnificent nebulae captured in images from the Hubble Space Telescope are composed of interstellar gas. Because this material exists throughout space, solitary neutron stars and black holes can begin to gravitationally attract it, pulling it onto themselves. This phenomenon is also known in astrophysics as accretion. In this scenario, matter is drawn toward a compact object, creating a situation somewhat similar to a binary system, just with a much smaller supply of material. Every gram of matter that falls onto a neutron star unleashes approximately 10 to the 20th power erg of energy, which is an immense amount. This energy release is a substantial fraction of what is liberated in a thermonuclear detonation, making accretion a remarkably simple yet highly efficient method for generating power. The concept of accretion onto isolated neutron stars and black holes was intensely debated in my country during the early 1970s. The true pioneer in this area was Igor Shvartsman, who published a series of papers between 1970 and 1971 that are still highly relevant today. Unfortunately, despite Schwarzman's own considerable efforts, which included searching for these objects from the Caucasus, all attempts to find such sources have so far failed. Even though a capture rate of just 100 billion grams per second would create a noticeably bright source, which, by astronomical standards, is a tiny amount of matter, we have yet to observe accretion onto a solitary neutron star or black hole. Detecting them remains a crucial objective for the near future. The next major Russian space-based astrophysics project is the Spectrum Röntgen Gamma satellite, which carries the German eRosetta telescope. This mission will perform an all-sky survey in X-rays, raising hopes that it will finally begin to identify these solitary accreting objects. The situation with black holes is slightly different, as they have no surface for matter to impact and create a bright flare. However, material falling toward a black hole can form a disk around it, and we hope to observe the radiation emitted by this disk. This also requires a comprehensive sky survey, but likely in different wavelengths, such as infrared or even radio waves, rather than X-rays. Some scientific studies suggest that future large-scale radio telescopes will be the first instruments capable of identifying lone, accreting compact objects. The expectation is that the physics governing accretion is similar enough in these cases that highly sensitive equipment will pick up the radio signals from these solitary bodies. However, another fascinating method for detecting an object, even one that is entirely invisible, is gravitational lensing. This is, in fact, a universal technique for studying any kind of matter because of one inescapable property: its mass. Everything has mass, whether an object is composed of iron, hydrogen, quark matter, or even dark matter. This principle is most evident when you consider a black hole, which possesses a truly remarkable quality. Regardless of what you feed into it, the outcome is fundamentally the same. You can form a black hole from any substance, including the most exotic particles imaginable, and it will still possess a certain mass. Consequently, any massive object inevitably warps the space surrounding it, and we can detect the effects of this distortion. To grasp this idea, imagine you could travel across interstellar distances. You would eventually feel something pulling you toward a specific point in space. From a distance, nothing appears to be there, yet you start to experience a gravitational pull. This happens because space itself is warped, and you are, in a sense, rolling down into this gravitational well. It isn't just you either. Everything that travels through this region, including light, follows the same distorted path, which is the core principle behind the incredible effect of gravitational lensing. This phenomenon was predicted by Einstein shortly after he formulated the general theory of relativity. While scientists had previously speculated that light rays might bend near massive objects, general relativity provided exact numerical forecasts and a much more accurate, entirely new interpretation. The first opportunity to verify this theoretical prediction arose during the solar eclipse of 1919. The test required astronomers to measure the positions of stars when their light traveled to us unobstructed, and then measure them again when a massive object, the sun, was in the way. According to the forecasts of general relativity, the images of the stars should appear to shift by a specific amount, dictated by the mass of the intervening object and the star's angular distance from it. For the first measurement, you can use observations from any clear night or simply consult reliable star maps and catalogs. But to measure the stars' positions as their light passes near the sun, you need a special situation. During a solar eclipse, it becomes possible to observe stars that are extremely close to the solar disk, which is precisely what scientists did, finding that the predictions of general relativity aligned remarkably well with the observational data. This success led specialists to ponder whether a similar effect could be observed if another star were to pass between us and a more distant one. Later on, the phenomenon of gravitational lensing caused by stellar mass objects came to be known as microlensing. One of the initial articles discussing this lensing effect was published in 1924 by the Russian scientist Orest Khvolson. When this happens, there are two observable consequences you can look for. The first effect is the one I have already touched upon. The apparent location of the background star in the sky shifts slightly. The second effect is even more straightforward to observe, as the star you are monitoring grows brighter, because the gravitational lens functions like a magnifying glass. The light from the distant star is focused, concentrating more of it toward your telescope. So, when you measure the star's brightness, you see its radiation intensity increase at the moment an object acting as a lens passes in front of it, and then decrease back to its original level as the lens moves away. It sounds simple enough, but you might wonder how likely such an event is. Einstein himself performed the first estimations between 1912 and 1915, well before his more famous 1936 paper on the subject. These calculations, which were later discovered in his rough notes and are detailed in an article by Tim Sauer available on Archive, explored whether lensing could be the explanation for the phenomenon of novae. We now know these are actually binary star systems where matter accumulating on the surface of a white dwarf triggers a thermonuclear explosion. It became clear that lensing had no connection to novae. For one, the light curves have different shapes. A lensing event should produce a curve that is symmetrical across all colors, whereas novae exhibit asymmetrical curves. Furthermore, novae outbursts occur far too frequently to be explained by such rare alignment events. In fact, to see just one microlensing event per year, you would need to be monitoring millions of stars simultaneously, a task that was technically impossible for more than 50 years while astronomers relied on photographic plates. A pivotal contribution to the advancement of the microlensing method came from Bohdan Paczynski in the 1980s. It was he who first recognized the immense potential of using charge-coupled device matrices, or CCDs, to observe this phenomenon, and he also originated the term microlensing. A modern CCD matrix is defined by its megapixels, meaning it contains millions of elements that capture an image. This technology is incredibly convenient because if you have a field of view packed with stars in a CCD image, you can track the brightness of millions of them at the same time. As soon as this technological capability emerged, researchers began actively hunting for the gravitational microlensing effect, and it wasn't long before they found it. This technique allows you to determine the mass of the object serving as the lens. It turned out that in certain instances, the object's mass is quite substantial, for example, 10 solar masses, or even more. If this were a typical star with a mass of 8 to 10 times that of our Sun, it would be exceptionally bright and therefore easily seen. And yet, observations revealed that the lensing object is completely dark. Within our galaxy, the only known dark compact object that could possess such a high mass in our vicinity is a black hole. Although several promising candidates for isolated black holes currently exist, with more added through microlensing observations in September 2015, they present a significant challenge. The issue is that lensing is a singular event. A black hole passes between us and a distant star, and then it's gone, preventing any observation before or after the fact. This makes it impossible for us to definitively verify that the object was, in fact, a black hole. While we have strong candidates for black holes within binary star systems, reliably confirmed solitary black holes or ancient neutron stars remain elusive, posing a challenge for future astronomical research. There is renewed optimism, however, thanks to the Gaia satellite, which may be able to spot these objects through the microlensing effect. Gaia's primary mission is to precisely measure the positions of stars to build a three-dimensional map of our galaxy, and in doing so, it should notice the gravitational distortions caused by unseen objects, like neutron stars and black holes, offering a fresh method for observing these captivating cosmic phenomena. Whenever we delve into a topic, it's always compelling to explore the most extraordinary examples. Just as people who post cat photos online are especially drawn to the most unusual and peculiar felines, among neutron stars, the most exceptional specimens are undoubtedly magnetars. The concept of the magnetar, the very idea of its existence, was formulated, as is often the case in science, only after evidence of them was first discovered. The story behind the conceptualization of the magnetar began in the early 1990s, when two separate research papers proposed the existence of neutron stars with extraordinarily powerful magnetic fields. In one of these studies, Vladimir Husov utilized this concept to explain cosmic gamma-ray bursts, a phenomenon that had mystified astrophysicists for nearly 30 years. These bursts were first detected by American reconnaissance satellites, the kind likely referred to as spy satellites in the USSR, which were originally designed to monitor nuclear tests. Though initially detected by American satellites, later observations from Soviet and Chinese spacecraft also recorded these gamma-ray flashes appearing from deep space. For 2 decades, from the late 1960s to the late 1980s, scientists were completely in the dark about the nature and origin of these bursts. This profound mystery generated enormous interest and led to a wide array of hypotheses, from theories suggesting they occurred within our own solar system to the idea that they were distant cosmological events, a conclusion that was eventually proven correct. Vladimir Husov's proposal was one of the key ideas about the nature of these cosmic gamma-ray bursts. He theorized that a neutron star could be born with an incredibly intense magnetic field, on the order of 10 to the 15th power Gauss, which is 1,000,000 billion times stronger than the magnetic fields of Earth or the Sun. His second premise was that this newly formed compact object would rotate at an immense speed, completing a turn in just 1 millisecond, near the physical limit for neutron star rotation. This combination would create an incredibly powerful energy source, fueled by the neutron star's rapid spin. Because of the extreme magnetic field, this rotational energy would be radiated away very quickly, much like a super radio pulsar, causing the rotation to decelerate rapidly. Consequently, what we would observe is a relatively short flash, a brief burst of activity with a swift decay in brightness. The radiation from such an object could be highly focused, concentrating a large part of its energy into the highest end of the spectrum, and thereby creating a gamma-ray burst. Another foundational paper, published in 1992 by Christopher Thompson and Robert Duncan, proposed a mechanism for how neutron stars with such extremely strong magnetic fields, hundreds of times more powerful than those of typical radio pulsars, could form. They continued to build upon this idea in subsequent articles, effectively inventing the modern concept of magnetars as objects that could account for various astronomical sources. It was they who also introduced the term magnetar to the scientific lexicon. Among the phenomena they sought to explain The most significant were the so-called soft gamma repeaters. In their initial 1992 article, Duncan and Thomson suggested that magnetars could be the source of these events. Curiously, the discovery of magnetars is intrinsically linked to these soft repeating gamma-ray bursts, which were first identified as a distinct class of objects associated with neutron stars back in 1979. In my personal view, this represents one of the most elegant discoveries in the history of Soviet and Russian astrophysics. It is arguably the most important and certainly the most beautiful finding made by their scientists working with satellite data. The pivotal moment occurred on March 5, 1979, when a gamma-ray source erupted in the direction of the Large Magellanic Cloud, a neighboring dwarf galaxy. Later analysis confirmed that the source was indeed located within that galaxy. A thorough investigation required some time, but eventually, Soviet-French instruments aboard the Venera probes operated by Yevgeny Mazets's scientific group at the Yoffe Institute made a breakthrough. They observed that following the initial intense peak of radiation, the source settled into a strict periodicity of several seconds. This rhythmic pulse was a clear giveaway, pointing directly to a neutron star, as few objects in the universe can maintain such a stable period. We now know for certain that this was an isolated neutron star, responsible for generating those incredibly powerful gamma-ray flashes. The initial burst of light was of such staggering intensity that our instruments were completely overwhelmed, unable to record its maximum brightness. In that fleeting moment, the magnetar outshone an entire galaxy, unleashing all of its energy in the form of hard X-rays and soft gamma rays. Following that event, we have witnessed two other magnetars emit colossal flashes that were followed by long pulsating radiation tails. The first of these, in August 1998, bore a strong resemblance to the March 5th event, but the subsequent flare on December 27, 2004, left everyone stunned. This magnetar outburst, designated SGR 1806-20 in the Sagittarius constellation, was so powerful it was dubbed a hyperflare. Its structure mirrored the great flares of 1979 and 1998, yet its energy output was 100-fold greater, blinding nearly every space-based X-ray and gamma-ray observatory pointed toward the Sun. The sheer volume of quanta saturated the detectors, making a direct observation impossible, but a single instrument managed to catch a glimpse of the initial blast. This was once again a device from the CONUS experiment, led by Yevgeny Mazets's group at the Yoffe Institute. At that moment, one of their instruments was aimed at the burst and was instantly blinded, while their second was shielded by the Earth's shadow, preventing it from seeing the flare at all. However, while processing the data, scientists discovered a faint signal that had arrived just seconds after the hyperflare. After some thought and calculation, they reached a remarkable conclusion. They had observed the burst reflected off the surface of the Moon, the only conceivable way to witness the event without being overwhelmed by its direct gaze. Naturally, eruptions of this magnitude ought to be detectable from across intergalactic space, but we face several challenges. For one, pinpointing the source at such vast distances after the flash has faded is next to impossible. Additionally, a magnetar flare's main peak looks very similar to a short gamma-ray burst, making them easy to mix up, and the coordinates for these solitary short bursts are often not determined with enough precision. Despite these difficulties, several promising candidates for extragalactic giant and hyperflares do exist. One of the most intriguing was identified by astrophysicists from the Yoffe Institute. when Dmitry Fredericks and his team spotted a flash coming from the direction of the Andromeda Nebula. While we lack definitive proof that this was a magnetar, its characteristics are highly suggestive. My own research with Boris Stern has shown that it's currently impossible to state with certainty which gamma-ray bursts are definitively linked to distant magnetars, primarily because we can't observe them after the initial event. Subsequent observations of all known magnetars, including the trio responsible for the powerful flares, revealed new outbursts, making it clear these are not catastrophic one-off phenomena. Whereas a magnetar might outshine a galaxy for an instant during a giant flare, its weaker bursts still make the neutron star tens of millions of times more luminous than our Sun. These less intense events can happen with surprising frequency. Some magnetars in their active phases can generate around 100 flares in a single month. Ultimately, rapidly discharging a tremendous amount of energy within a tiny volume is an immense physical challenge, and it is even more difficult to do so without obliterating the object itself. In an interview, an actor once explained that when performers insisted they could do their own dangerous stunts, one was asked if he could jump from a 5-story building. He replied, "I can, but only once." Many cosmic explosions, such as supernovae, are exactly like that. They only happen a single time. This is why developing a model for an object that could repeatedly unleash more energy than an entire galaxy proved so difficult. Eventually, we discovered that such incredibly resilient objects do exist, and we call them magnetars. The prevailing model from the 1990s describes them as neutron stars possessing enormous dipole magnetic fields, which are maintained by extremely powerful electrical currents flowing deep within the compact object. These currents might flow within the neutron star's core, which is composed of relatively conventional matter. Just as a current can gradually release energy by heating a coil, it can also discharge it explosively through a short circuit. If you could create a short circuit on a neutron star, the result would be an immensely powerful flare, which is precisely what we observe as a source of soft, repeating gamma-ray bursts. While the magnetar model neatly explains these violent outbursts, it also allows for mechanisms of gradual energy release, which brings us to their relatives, anomalous X-ray pulsars. In the mid-1990s, several scientific groups studying X-ray pulsars identified a new class of solitary neutron stars, which turned out to be the cousins of the soft gamma repeaters. Before this discovery, all known X-ray pulsars were thought to be binary systems, consisting of a neutron star and a regular companion star. In these systems, material from the ordinary star is siphoned off by the neutron star, and the immense heat generated by this falling plasma produces a powerful stream of X-ray radiation. As you might recall, a neutron star's magnetic field funnels this incoming matter toward its polar caps, much like Earth's magnetosphere guides charged particles to our planet's polar regions to create the auroras. As the compact object spins on its axis, we alternately see one polar cap and then the other, giving rise to the pulsating X-ray signal that defines a pulsar. However, further research uncovered a strange collection of X-ray pulsars that were different from all the others. To give away the conclusion, these were later identified as magnetars. These peculiar X-ray pulsars all shared remarkably similar rotation periods, which was unusual, because the periods of typical X-ray pulsars can vary widely, from mere milliseconds to several hours. Their brightness registered at approximately 100 times dimmer than that of their counterparts. Unusually, their rotation period only ever increased, whereas for the majority of X-ray pulsars, it would either accelerate or decelerate. Furthermore, there were no detectable signs of radiation linked to any orbital movement, which led to the conclusion that these were, in fact, isolated neutron stars. This meant there was no transfer of matter, a process scientifically known as accretion, taking place. Instead, the neutron star itself possessed intensely hot polar caps. The challenge was to explain why this occurred, and the answer lies in powerful magnetic fields. It's a phenomenon involving the steady release of current energy, not through a sudden short circuit, but gradually, much like the process inside a kettle or an electric space heater. The temperature is always highest at the location of the heating element where the current flows, and from there, the warmth disperses throughout the entire volume via thermal conduction. In a similar way, a neutron star's surface can be heated unevenly, with the poles becoming significantly hotter because heat from the core is transported by electrons, which travel more easily along the magnetic field lines that converge at the surface of the poles. For a period, the hypothesis that accretion could be responsible for the glow of anomalous X-ray pulsars was seriously considered. This scenario would have necessitated a substantial accretion disk, where matter accumulated right after the supernova explosion could have accounted for the source's luminosity and spin periods. This theory, however, fails to explain certain characteristics of their outbursts. Crucially, it was discovered that some of these pulsars can generate weak bursts that closely resemble those seen in sources of soft repeating gamma-ray bursts. Interestingly, between their own explosive events, sources of soft repeating gamma-ray bursts can appear quite similar to anomalous X-ray pulsars. This observation prompted some scientists to theorize that the two were related phenomena, with an exceptionally strong magnetic field serving as the unifying element. But why is the emphasis specifically on strong magnetic fields for both of these object types? Technically, even modest magnetic fields could result in some areas of a neutron star's surface being hotter than others, and a short circuit could theoretically be engineered without extreme magnetic forces. However, when the fields are immense, the currents they generate are also immense, leading to a greater release of energy that makes these objects far more conspicuous, which is the first reason for the focus on strength. A second reason, which I won't delve into deeply, is that powerful currents evolve more rapidly and observably, meaning their rate of energy dissipation is significantly higher. A thorough exploration of this point, though, would demand a complex discussion of the underlying physics with all the accompanying calculations. The third justification comes from the direct measurement of their magnetic fields. Regrettably, directly gauging the magnetic fields of such distant objects is quite a difficult task, so they are measured indirectly and as a group. A neutron star that isn't interacting with surrounding material will slow its rotation faster if it has a stronger magnetic field. By observing this rate of rotational deceleration, we can infer the field's strength. While this method is very effective for radio pulsars, applying the same technique to soft repeating gamma-ray sources and anomalous X-ray pulsars reveals that their fields are hundreds of times more powerful, with the interplay of their rotation period and slowdown rate being tens of thousands of times more effective. There are additional compelling arguments for the immense magnetic fields of magnetars. One can calculate the energy reserves required to sustain their flare activity over tens of thousands of years, and the necessary amount aligns perfectly with the energy stored in a massive magnetic field. To create the pulsating tail seen after a giant flare, something must prevent the matter from dispersing, a task that can be accomplished by an incredibly strong magnetic field. Ultimately, The spectral data from magnetars also provides strong evidence in favor of this model. An exquisite result was delivered by the Integral X-ray satellite, initially by Sergei Mulkov and his collaborators, and later confirmed by other observer teams. Prior to these observations, no one had managed to capture a magnetar's spectrum at energies much higher than 10 kilo-electron-volts, which is beyond the standard X-ray band. Projections from existing spectra and their corresponding theoretical models had predicted that the sources would be faint in the hard X-ray region. It turned out this was incorrect. Several anomalous X-ray pulsars and soft gamma-ray repeaters displayed powerful radiation in this very range. Although various models emerged to explain these findings, the most successful ones all depend on the presence of a powerful magnetic field. From this body of evidence, the initial modern concept of magnetars took shape. They are neutron stars defined by magnetic fields that are enormous in both their magnitude and their spatial reach. They are also quite uncommon, with known magnetars being about 100 times less numerous than radio pulsars. The simple reason for this is that their lifespan as active objects is not very long, lasting tens of times shorter than the radio pulsar stage, before they exhaust their energy and fade from view. It is now thought that several percent, perhaps as high as 10%, of all neutron stars may pass through such a magnetar phase in their youth. As soon as this first concept of magnetars emerged, the question of their origins naturally arose, given that ordinary radio pulsars are the standard. The initial papers by Thomson, Duncan, and their colleagues proposed that the answer was rooted in the dynamo mechanism. To help you visualize this, I can explain the idea this way. We all tend to picture magnetic fields as lines of force, almost like invisible cords that protrude from a magnet. Imagine twisting and folding a simple cord, which causes it to become much more densely packed in a specific area. A magnetic field behaves in a similar fashion. If you manipulate its lines of force in the same way, its strength will double. For this to happen, the field must be intimately linked with matter, and that matter needs to be undergoing very particular kinds of motion. Within a magnetar, this necessary three-dimensional motion can occur under two specific conditions. First, the neutron star must be spinning at an incredibly high speed. And second, it must still exist in a liquid state that permits convection. When these factors are present, the combination of convection and rotation inside the proto-neutron star can amplify magnetic fields via what is known as the dynamo mechanism, which requires rotation speeds tens of times greater than those of typical pulsars at their birth. So, what could possibly make a newborn neutron star spin with such extraordinary velocity? The speed of its rotation is intrinsically tied to the rotation of the star from which it originated, known as the progenitor star. A promising method for spinning up a progenitor involves a binary star system, where gravitational interactions with a companion can force it to rotate several times faster than it would alone, eventually collapsing into a rapidly spinning neutron star with an immense magnetic field and becoming a magnetar. Whether this binary interaction model is definitively correct remains an open question, but it provides a coherent logical sequence for the creation of neutron stars with exceptionally powerful magnetic fields, in roughly 10% of all cases. Furthermore, we have observational data that hints, at least in some instances, that magnetars did indeed originate from progenitor stars that were spun up at some point in their evolution, through their presence in binary systems. This entire picture, however, is becoming increasingly intricate. Initially, Magnetars were categorized either as sources of soft repeating gamma-ray bursts or as anomalous X-ray pulsars, leading to the belief that these were two entirely separate classes of neutron stars. Yet, the more time we spend observing them, the more we uncover profound connections linking the various types of these stellar remnants. A firm relationship was first established between anomalous X-ray pulsars and the sources of soft repeating gamma-ray bursts. This connection became clear through two key discoveries. Nearly all soft repeating gamma-ray sources behave like anomalous X-ray pulsars in the quiet periods between their outbursts. And conversely, long-term observation revealed that anomalous X-ray pulsars can erupt with flares characteristic of soft repeating gamma-ray bursts. Scientists were then confronted with even more astonishing developments. It had long been accepted that classical magnetars did not produce radio emissions like standard radio pulsars, and theories were built around this absence. But then, such emissions were detected, proving that a magnetar could indeed function as a radio emitter. More recently, during the 2000s, a radio pulsar was observed transforming into a source of soft, repeating gamma-ray bursts, which necessitates a new evolutionary framework to explain how one object type can morph into another. In contrast to conventional magnetars, which are identified by the rapid breaking of their spin due to powerful dipole magnetic fields, astronomers have recently found flaring neutron stars whose periods change very slowly. These objects produce bursts just like soft repeating gamma-ray sources and have similar rotation periods, yet estimates of their magnetic fields, based on spin-down rates, suggest they are about 100 times weaker, comparable to ordinary pulsars. The discovery of several such sources brought considerable satisfaction to those who questioned the standard magnetar model. While the large-scale dipole component of a magnetar's field is what governs the change in its rotation period, powerful and complex multipolar fields near the surface are crucial for other phenomena. The decay of electrical currents within the magnetar's crust releases energy, heating the surface through a process called reconnection. When Andrei Tulbashev and his team used the XMM Newton X-ray Observatory's large collecting area to get a high-quality spectrum of a magnetar with a weak dipole field, they found spectral details pointing to an incredibly strong, localized field near the star's surface, perfectly aligning with the multipolar field model. Ultimately, it seems that the diverse phenomena observed in the alchemy of neutron stars are connected to the decay of their magnetic fields. This is an entirely logical concept, as a neutron star has no internal power source. The electrical currents inside it are destined to weaken over time. This decay process can alter the neutron star's state, causing it to flare with varying frequency or to cease flaring altogether. A plausible evolutionary timeline suggests an object could be born as a source of soft repeating gamma-ray bursts, later evolve into something resembling an anomalous X-ray pulsar, and finally, as its magnetic field fades further, become a quiet neutron star, visible to us only through its residual heat. We currently know of only 7 such sources in our cosmic neighborhood, a group famously referred to as the Magnificent Seven. Significant efforts have been made to construct a single, unified evolutionary scenario that encompasses these different classes of neutron stars. The first successful attempt was a collaborative effort between my colleagues from Spain and Germany and myself. Using a cohesive approach, we were able to account for classical magnetars, the Magnificent Seven, and similar objects, and even ordinary radio pulsars within the same framework. As our research progressed, even more remarkable transformations came to light, allowing us to forge links with other kinds of young neutron stars. For instance, We observe central, point-like objects within the remnants of supernovae. We are certain that these are newly formed neutron stars, visible to us simply because they are still intensely hot from their birth only a few thousand years ago. In contrast to magnetars, these objects can possess incredibly brief periods, measured not in 5 to 10 seconds, but in mere tenths of a second. A very compelling idea gained traction in the second decade of this century, suggesting that a neutron star with a powerful magnetic field, a magnetar, is born first. However, following the supernova explosion, a portion of the material collapses back onto it, burying the magnetic field under so much matter that it becomes shielded. For several thousand years, you might be completely unaware that a magnetar is concealed within. The external magnetic field would appear remarkably weak, even more so than that of typical radio pulsars, causing its rotation to slow down very gradually. It would, however, be unusually hot, because the magnetar is effectively hidden inside a cocoon. Detailed analysis of these objects suggests this is an extremely fruitful hypothesis, representing a phenomenon that could genuinely occur in nature. It appears that some X-ray sources found in supernova remnants are precisely these kinds of buried magnetars, which require several millennia to emerge and transform into a beautiful spectacle. The concept of a grand unification for neutron stars, a bit like linking hares and squirrels, is a common thread in all natural sciences, and even to some degree in less natural fields. There's a persistent drive toward creating a single, cohesive picture, which involves not just classification, but an effort to explain everything from a common starting point using a universal set of laws. This progression is characteristic of any scientific discipline. The most prominent illustration of this, of course, is the development of unification theories within physics. At one time, electricity and magnetism were considered entirely separate forces, but they were eventually combined into the theory of electromagnetism. Subsequently, the electromagnetic and weak interactions were unified, and later the strong nuclear force was incorporated. While a final complete theory that includes gravity, often called a theory of everything, remains elusive, one can identify two primary drivers for this tendency toward unified models. You can think of these drivers as a carrot and a stick. The first, which is discussed more frequently, relates to an aesthetic impulse. There is an undeniable beauty when facts and ideas that seem completely unrelated suddenly click together to form a coherent mosaic. This is intertwined with the aesthetic conviction that the universe is structured with relative simplicity, allowing us to describe or comprehend it, and to hold this elegant construct within our minds. For this reason, many are persuaded that unifying frameworks must be the correct path. However, I believe there's likely a second, more subconscious motivation that holds greater significance at a collective level. When faced with a profusion of phenomenological theories and a vast number of disconnected problems, we start to worry that this avalanche of information will simply overwhelm us and halt further progress. It becomes impossible to operate effectively with such a scattered collection of data and to keep so many separate pieces of the picture in focus. If the specific could be derived from the general, it would empower us to gather new data and solve new problems until we reach the next frontier, where a new unified theory can emerge. It seems to me that the allure of pseudoscience or mythological explanations for phenomena is also linked to these two motivations. First, such explanations are often elegant and simple, and second, the thought that everything might be overwhelmingly complex can be quite frightening. This anxiety encourages the acceptance of a straightforward, even if incorrect, picture of the world. Models that aim for a unified description are typically built upon some shared characteristics of the objects they seek to explain. It works even better if the components of the system can transform into one another, or display properties that are typical of several different classes at once. When evolution is present within a system, new avenues for unification open up. In our own lives, for instance, you know that hares don't evolve into squirrels, but we understand that both share a common ancestor. In this way, biology also works to explain everything from a unified perspective, and the evolutionary model makes this possible. Therefore, the ambition to explain a wide diversity of objects within a single framework is universal, and the astrophysics of neutron stars is certainly no exception. To unite these seemingly disparate types of neutron stars, it was first necessary to separate them decisively. Initially, the classification of neutron stars was quite clear. The first to be found were pulsars, which are young neutron stars that spin rapidly. They possess a rather strong magnetic field that generates what is known as coherent non-thermal radiation in their magnetosphere, which includes radio emissions. There are pulsars you can observe pulsating across the entire electromagnetic spectrum: invisible light, infrared, ultraviolet, X-ray, and gamma-ray ranges. Soon, astronomers began discovering other kinds of young neutron stars, such as magnetars. This discovery stands as one of the most stunning astronomical achievements ever made in our country. On March 5, 1979, the CONUS experiment aboard the Venera space probes detected an incredibly powerful gamma-ray burst. After the initial burst, the brightness didn't fade to nothing. Instead, pulsations with a period of several seconds appeared. Astronomers quickly identified the source as a neutron star, pinpointed its location, and established that it was a young object, adding a completely new type of activity to the list of observed behaviors for compact objects. This collection of cosmic objects continued to expand, and by the close of the 1990s, there were roughly half a dozen distinct classes of young neutron stars, each manifesting as a very different kind of astrophysical source. The prevailing thought was that each one was fated to be born as a particular type: a radio pulsar, a central compact object in a supernova remnant, or something else entirely, and that was its unchangeable destiny. But then, new observations started to emerge that would challenge this entire picture. It has become clear that an astronomical object is by no means confined to displaying a single kind of behavior. For instance, hares can seemingly transform into squirrels and back again. We observed a radio pulsar, which had been seen exclusively as a source of that type, when it suddenly started emitting bursts characteristic of a magnetar, effectively shifting from one classification to another. Additionally, scientists began discovering transient magnetars, temporary sources that exhibit intense activity for a period, perhaps flaring for a while, before falling silent for much longer durations. If we happen to discover and observe a magnetar during its active phase as a source of soft repeating gamma-ray bursts, it might behave like a completely different class of object during its quiet phase. Despite this variety, we are certain that all these objects are young neutron stars. As more and more data like this accumulated, revealing ever deeper connections between different types of neutron stars, a powerful scientific impulse emerged. This was a drive, rooted in tangible observational evidence, to unify all these phenomena under a single comprehensive scenario, a grand unification for neutron stars. The goal was to use a single set of physical laws and one evolutionary framework to explain the entire spectrum of source types. The central question that arises from this The key connecting element concerns how the evolutionary links between these different types of objects are structured. Is there just one possible path? A strictly defined sequence of stages? For example, could an object be born as a magnetar, later manifest as a cooling neutron star similar to those in the Magnificent Seven, and then become a radio pulsar? Or are other developmental scenarios possible? And if there are different paths, what parameters or combinations of parameters are responsible for them? When we discuss evolution, we are fundamentally talking about changes in certain properties of a neutron star. From an astrophysical standpoint, a neutron star is a relatively simple object, described by a surprisingly small number of parameters that dictate its primary behaviors. Let's examine what these parameters are. First, there is mass. The mass of actual neutron stars is restricted to a very narrow band, ranging from about 1 to 2 times the mass of our Sun. The lower boundary is set by the characteristics of stellar cores and the gravitational mass defect. While a cold neutron star could theoretically have a mass as low as 0.1 solar masses, such objects don't form from core collapse. Instead, the cores of low-mass stars become white dwarfs. The upper limit is defined by the point at which matter becomes unstable and undergoes a final collapse into a black hole. For single stars, we can assume with great confidence that the mass is constant, so you can't build an evolutionary story around it. Second is velocity, the speed at which the neutron star travels relative to its cosmic neighbors and the surrounding interstellar medium. While we know that different types of objects can have vastly different speeds, a neutron star cannot be rapidly accelerated or decelerated. This means that, much like mass, velocity is not a viable basis for explaining its evolutionary changes. The next significant parameter is its rotation period, which influences many of its characteristics. We know this property evolves dramatically, but for isolated objects, the change is almost always in one direction. They spin slower and slower over time, as there isn't a readily available mechanism to speed them up again. Consequently, you cannot construct a complex evolutionary narrative based on changes in its period. Then there is temperature, which is admittedly more complicated. The general trend is for the object to cool down, but a neutron star can possess internal heat sources that enable it to either stay hot for an extended period or even heat up over time. However, even though its temperature can change significantly, it's unlikely to be the direct cause of abrupt shifts in a neutron star's behavior. Instead, temperature is more of an indicator of other changes, much like the clock at a train station. The train doesn't arrive because the clock shows 11. The clock merely tells you when the train is scheduled to arrive, and you could remove it, stop it, or reset it without affecting the train itself. This leaves the neutron star with one crucial parameter that varies significantly over time and between objects: its magnetic field. Neutron stars possess powerful magnetic fields, and by powerful, I mean they reach exceptionally high values. For context, the average magnetic field on the Sun's surface, outside of sunspots, is about 1 Gauss. By contrast, the magnetic field at the surface of a neutron star is roughly 1,000 billion times stronger than on the Sun or Earth, and in some cases, it can even be 1,000,000 billion times stronger. There are a couple of reasons for this immense strength. The first is fairly straightforward. A neutron star is created from the collapse of an ordinary star's core, and the magnetic field gets amplified during this collapse. As the matter is pulled inward, it drags the magnetic field lines with it, compressing them. You can visualize this by thinking of the magnetic field lines we all drew in school, creating a butterfly shape around a simple magnet. Now, picture that you've drawn this and then start shrinking the drawing. The number of field lines passing through the collapsing core, the proto-neutron star, remains the same, but the area they pass through becomes vastly smaller, which corresponds to a massive increase in the magnetic field's strength. However, there is also a second reason. It appears that this first mechanism of simple compression is not sufficient on its own to account for the magnetic fields of the most extreme neutron stars. To explain the fields of the most highly magnetized objects, such as magnetars, it seems some special process of magnetic field amplification must also be at work during their formation. We don't yet understand the precise mechanism, but its existence seems apparent, which presents a significant challenge. We must define and characterize it using the language of physical theory. The magnetic field, therefore, stands out as a promising parameter, one that is potentially subject to fascinating variations. For a long time, however, it was assumed that its evolution must also be straightforward. The most basic form of evolution is none at all, where the parameter is simply constant, while a slightly more complex version involves decay. You and I are accustomed to seeing things break down when there's no energy source or other factor to counteract the decline. To understand this, you need to remember the origin of magnetic fields in the first place. A neutron star isn't a magnet in the conventional sense, meaning it's not some piece of iron colored blue on one end and red on the other. Whereas the field of an ordinary magnet arises from currents at the molecular level, the magnetic fields of neutron stars are produced by macroscopic currents. So, when we discuss these fields, you should envision immensely powerful currents flowing deep inside the neutron star, which in turn generate the magnetic field you observe. This concept grants theorists considerable room for creative thought, as it implies that these internal currents can be strengthened or weakened. One can devise processes that would alter these currents over time. While the overall trend is naturally toward a decrease in their intensity, their evolution can follow intricate paths. It's not just their strength that can shift, but also their underlying structure. Furthermore, it's possible for the magnetic field to be shielded. If you were to envelop the neutron star in a shell of conductive material, you might not detect the field from the outside, or you might see it as substantially weaker, a mechanism that surprisingly finds application in astrophysics. As a result, a new picture of neutron stars is taking shape, with all the primary theories centered on the evolution of their magnetic fields, proving it to be a remarkably effective parameter. The fields vary dramatically among different classes of objects. They are most powerful in magnetars, less so in pulsars, and weaker still in the central compact objects found within supernova remnants. Moreover, the magnetic field can exhibit what are known as different topologies, or to put it simply, different shapes. It could be a very basic field, resembling the butterfly pattern of a magnet from a school science kit, or it might feature small, intense loops of a strong field confined close to the surface. This complexity means that from a distance, you might observe a field that doesn't seem particularly strong, while up close to the surface, it could be immense. The field can also become twisted and tangled, a configuration that triggers the release of additional energy and gives rise to transient magnetars. In these cases, the magnetic field evolves as one of its components intensifies, and then its energy is suddenly and violently discharged. You can think of it as a series of short circuits occurring within the neutron star, causing it to erupt with a volley of flares. Once this burst of activity subsides, the average field strength diminishes, and you might observe the object as nothing more than an ordinary radio pulsar. In recent years, astrophysicists have zeroed in on an evolutionary mechanism I've already touched upon, which may supply the final, critical link connecting the various types of neutron stars. This particular scenario allows for an increase in the magnetic field of compact objects that you observe in key astrophysical events. It unfolds like this. You start with a massive star, which, at the end of its life, undergoes a supernova explosion. While its outer layers are blasted away, its iron core collapses to become a neutron star. So far, the process is standard. However, not all of the ejected material necessarily escapes into space. Some of this matter, which is an excellent electrical conductor, can fall back onto the star. The magnetic field induces currents within this conductive layer, effectively canceling out the field for an external observer. Such a situation can occur if a sufficient amount of material falls onto the neutron star, pressing its magnetic field down against the surface. The result is a truly fascinating object. Internally, you could have a neutron star with an incredibly powerful field, sustained by massive currents. But externally, it's all concealed beneath a thick blanket of conductive matter. From a great distance, what you would perceive is an object with a very faint field. A star like this loses rotational speed very slowly and displays no signs of violent activity. You simply see a 10-kilometer sphere glowing at a temperature of around 1,000,000 degrees, appearing to be a completely placid object. Yet, concealed within, it could be anything, including a magnetar. One of the objects currently under intense study is a prime candidate for just such a buried or hidden magnetar. This discovery was made in a rather compelling way. The object is monitored in the X-ray spectrum, and its emissions are observed to pulsate. This doesn't mean the star itself is expanding and contracting. It simply has hotter regions on its surface. As the neutron star spins on its axis, you sometimes see more of this hot surface, and sometimes less, causing the amount of radiation reaching us to fluctuate. The observed pulsations are exceptionally strong, and when astrophysicists attempted to model this behavior, they found a contradiction. The field, as inferred from its rotation, appeared to be weak. The only plausible explanation is that the external field, which governs the neutron star's deceleration, is small. While deep within the compact object's core, immense currents sustain a powerful field that is hidden from us by this accreted material. This state, however, is not permanent. On the timescale of a neutron star's life, it's a relatively brief period. Over several tens of thousands of years, the field will eventually diffuse and push its way to the surface. Thus, a mechanism has been conceived, and observational evidence found to support it, that can transform the most tranquil neutron stars into the most turbulent. A neutron star can remain dormant for thousands or even tens of thousands of years, confined within a kind of straitjacket. Eventually, however, the star's magnetic field will inevitably erupt, and a magnetar will burst forth from this shell. If this process truly reflects what happens in nature, it provides us with evolutionary scenarios that connect all currently known classes of neutron stars, giving us a unified picture. The next step is to construct detailed computer simulations based on these scenarios to confirm that they align with our observational data. On the other hand, Observations over the last 2 decades have dramatically expanded the variety of known neutron stars, so we are psychologically braced for new revelations. It's entirely plausible that in a few decades, or perhaps even a few years, we'll discover some astonishing new objects that defy the framework we've constructed. Should that happen, the quest for a grand unification will have to press onward, seeking new evolutionary links between different kinds of compact objects, a task that might even require us to develop new physics. Compact objects and fundamental physics can be seen as the astrophysical laboratories for those without massive budgets. Leo Tolstoy wrote, "All happy families are alike. Each unhappy family is unhappy in its own way." Let's set aside the unhappy families for him to analyze, and focus on the happy ones. This statement has the ring of a universal law, but does it truly possess such a broad application? To be rigorous, it demands investigation and verification. Are happy families equally content in times of war and peace, or across cultures, from Kazakh to Filipino, and from Australian to Swedish? This is a question that requires proof. If you want to transition from literature to science, in this case sociology, you'll find that all scientific disciplines operate on a similar principle. When we formulate a law, which in astrophysics would be a physical law, we are obligated to test it under a multitude of conditions. The temptation is to believe that the book of nature is written purely in the language of mathematics, but the reality is far more complex. In truth, we experience the world directly. We don't just read about it, and we often look without truly seeing. Even when a great physicist has laid down a law centuries ago, there can be alternative ways its story continues. I recall a fascinating incident when the final Harry Potter book came out. I was at the Cagliari Observatory in Sardinia without internet access, and didn't want to buy the book because it was a long trip home. I ended up finding and reading what I thought was the original, but it was actually an alternative continuation. I have to say I enjoyed it more than the real final volume, though that one was also quite good. Having excellent alternatives is a wonderful thing, and it's especially crucial in the realm of science. Science as a whole thrives as long as we have the freedom to imagine and write different continuations for that book of nature Galileo spoke of. Take a well-established physical law, for instance, like the laws of electrodynamics. It's a subject that seems thoroughly understood. We started learning about it in school, completed our studies at university, and then likely forgot the details. But if you push these laws to the limit of extremely powerful fields, alternative possibilities begin to emerge. As we venture from the familiar territory of standard fields into the extreme domains of powerful ones, the path can diverge. Theorists, much like different authors, hold varying perspectives on how the universe is structured. This is why in the natural sciences, it's essential to verify which of the proposed alternatives actually matches reality. In other words, if you want to study happy families, you need to go out into the world, gather data, and determine if they are all happy in the same way, or if the initial hypothesis is flawed. Unfortunately, physical experiments always have their boundaries. There are always limiting values for the parameters you can achieve with any given setup. To start with a very basic example, if you are investigating gravity, you can measure its force within your room. You can then expand to the scale of our planet by launching satellites into Earth's orbit, and further still by sending probes throughout the solar system. But you cannot use laboratory equipment to probe the laws of gravity on vast, cosmic scales. For that, you must turn to natural phenomena. Sometimes we simply lack the power or the means to generate extreme parameters in a laboratory setting, which forces us to look toward natural, often astrophysical processes. It was with good reason that academician Zeldovich referred to the universe as a poor man's accelerator. For example, after immense effort, they built a massive accelerator and learned to propel particles to incredible energies. Yet, particles arriving from space every day free of charge possess energies 1 billion times greater than those achieved at the Large Hadron Collider, and we can, in principle, study them as well. Neutron stars represent just such unique natural laboratories, where a wide array of physical parameters are driven to their extremes, perhaps to the absolute limits that exist in nature. These objects allow us to probe new and mysterious phenomena. A few years ago, for instance, the Pamela instrument on the Russian satellite Resurs DK-1, designed to study cosmic rays, detected an excess of positrons. This discovery created a huge stir, immediately sparking the theory that these extra positrons might be a product of dark matter particle annihilation. This idea surfaced even before the formal publication of the PAMELA data, based on slides from a conference presentation, which ignited a separate debate about scientific ethics. For several months, roughly one new paper a day was published dedicated to this effect. However, there are complications with that theory. The prevailing belief now is that a better explanation for the surplus of positrons lies with nearby radio pulsars, which are known to contain vast quantities of electron-positron pairs. Detecting a surplus of electrons is quite challenging, much like noticing an extra spoonful of water in a bowl of soup. On the other hand, an excess of positrons is immediately obvious, similar to adding a spoonful of salt to that same soup. Neutron stars might also help us resolve another profound enigma known as fast radio bursts. You may recall our earlier discussion about rotating radio transients. Their discovery hinged on inventing and implementing technology that could pinpoint individual, extremely brief radio pulses lasting only milliseconds. As astronomers searched for these fleeting signals, they uncovered more than just flaring neutron stars. In 2007, Duncan Lorimer and his team detected one of these millisecond radio bursts. But nothing further was ever observed from that patch of sky. An analysis of the signal suggested it likely originated from intergalactic distances, though this couldn't be stated with absolute certainty, leaving room for debate and further investigation. A wave of different hypotheses immediately followed, with many implicating neutron stars, such as a magnetar. A second, comparable burst wasn't found until several years later, prompting its discoverers to propose a different origin: the evaporation of a black hole. This was precisely the kind of event that John O'Sullivan, the radio astronomy engineer who pioneered the technology behind Wi-Fi, had been hoping to find. Still, there were significant doubts about whether these were genuine cosmic events at all. These doubts were compounded by the observation of very similar signals called peritons, which clearly had terrestrial, not astronomical origins. However, in 2013, a paper by D. Thornton and his co-authors presented 4 new fast radio bursts, making it clear that this was indeed a real astronomical phenomenon. The situation grew increasingly reminiscent of the period from 1970 to the late 1990s concerning the mystery of cosmic gamma-ray bursts. The case of the peritons took an unexpected turn in 2015, when Emily Petroff and her colleagues in Australia demonstrated that these signals were recorded whenever a microwave oven was used at the park's observatory. This meant the phenomenon was not just terrestrial, but artificial, stemming from the improper use of radiating equipment at a radio astronomy facility. What's significant for us is that solving the periton mystery made the case for fast radio bursts as a genuine astronomical phenomenon much stronger. At present, the majority of astronomers concur that fast radio bursts are extragalactic flaring sources. A breakthrough occurred in 2014 when a burst was witnessed in real time for the first time, rather than being discovered in archival data. In the most promising models developed to explain this phenomenon, the source is a neutron star. In fact, Konstantin Postnov and I put forward one such model centered on magnetars, and the physical intricacies were later detailed in a study by Yuri Lyubarsky. There is a humorous theorem that can be proven with ease. Neutron stars are characterized by super-strong gravitational fields, super-strong electromagnetic fields, superconductivity, and superfluidity. In English, all of these terms begin with the prefix super. Thus, the theorem is confirmed. Neutron stars are truly super objects, which explains why physicists adore them and are willing to share their most precious asset, Nobel Prizes, with astronomers. Frankly, physicists sometimes look at astrophysicists' work with a hint of condescension. The reason is that the processes unfolding in astrophysics are entirely beyond our control. We are limited to observation, which is a world away from a direct, controlled experiment where we can actively manipulate the object of study. When you cannot directly interact with what you are researching, the results are naturally considered less reliable than if you had all the processes under your command. Nevertheless, there are times when observation is the only path forward. Neutron stars serve as a perfect natural laboratory, a place where we can witness exotic processes without any ability to interfere. While many exciting discoveries are made in astrophysics, not all of them are equally compelling for the field of fundamental physics. For instance, the discovery of exoplanets is unlikely to ever merit a Nobel Prize, as the consensus is that while it is a major finding, it remains too purely astronomical and has almost no connection to fundamental physics. The discovery of neutron stars, however, was instantly seen as being profoundly important to several branches of physics. For this reason, Nobel Prizes have been conferred for the discovery of neutron stars, radio pulsars, and the first binary radio pulsar system. At the end of this chapter, we will try to envision what other awards might yet be granted for the study of gravity beyond our terrestrial experience. So, what remarkable physical processes can we explore by observing neutron stars? And what are the unique conditions associated with them? The second Nobel Prize in this domain was awarded for the study of intense gravitational fields. Observations of binary radio pulsars have substantiated the predictions of the general theory of relativity for gravitational fields that are many times stronger than anything we can access within our solar system or on Earth. While the most powerful gravitational fields in principle exist near black holes, there is a major complication. A black hole lacks a surface. This makes it currently impossible to examine the behavior of matter near the event horizon. Although we observe a great number of black hole candidates, we are mostly just seeing the matter that is in orbit around the black hole itself. General relativity contains a very intriguing property. In conventional Newtonian gravity, if you place a small sphere on different orbits around a gravitational center, it can maintain a circular path, no matter how close it gets to the massive body's surface. A satellite can orbit a simple point mass at any distance. This does not hold true in general relativity, however, as there is a final, stable, circular orbit beyond which this is no longer possible. If you bring an object too close to a black hole, its orbit degrades into a spiral, causing the satellite to fall in rapidly. There's a distinct inner boundary to the accretion disk, but it doesn't extend all the way to the black hole's event horizon as you might assume. Instead, this boundary lies much farther out, potentially 3 times the distance of the horizon, depending on the black hole's spin and the disk's direction of rotation. Matter from this inner edge plunges into the black hole so quickly that it creates a void, leaving no bright region of superheated material to observe for any length of time, which makes it incredibly challenging to study what occurs in these regions of extreme gravity. A neutron star, however, can possess a radius smaller than this final stable orbit, meaning its accretion disk might also fail to reach the star's surface. The crucial difference is that the surface itself is solid and therefore visible, allowing us to observe it directly. This unique characteristic gives us a window into studying exceptionally dense matter and the principles of nuclear physics within the universe's most powerful gravitational fields. These investigations are all made possible by astronomical observations that continue to improve with remarkable speed. We are living in an extraordinary era where every 10 to 20 years we gain access to new instruments across all spectral ranges that outperform their predecessors by an entire order of magnitude in every key parameter. While the universe itself isn't changing, our ability to perceive it is transforming radically as we master new observational techniques. We can now detect gravitational waves and neutrinos, and we are even making attempts to look directly into the interiors of these compact celestial objects. Another property of neutron stars that is profoundly important to physicists stems from their incredible density, which causes matter in their cores to behave in astonishing ways. For instance, despite temperatures in the inner layers reaching 1 billion degrees or more, the matter there can enter a state of superfluidity. This condition allows us to witness a variety of fascinating effects, because a superfluid liquid rotates in a manner completely different from an ordinary one. If you were to take a glass of superfluid and start spinning it, the liquid itself would not rotate as a unified whole. Instead, it would form what are known as quantized vortices, a phenomenon that has been extensively studied in laboratory settings, and you can find excellent videos online demonstrating how these vortices appear. A neutron star functions very much like this glass. It's a massive object with a superconducting crust and inner layers of charged particles like protons that are linked to it, while the core contains superfluid neutrons. This creates a situation where the star's main mass spins as a single entity, but the superfluid neutron liquid within rotates in a completely separate manner, forming its own internal vortices with distinct rotational properties. Over time, a neutron star's rotation gradually slows down due to the influence of its external magnetic field, which generates currents that act as a brake. The star's crust decelerates, but the superfluid inside is initially unaware of this change and continues to spin rapidly. This discrepancy in rotational speeds cannot build up forever. Eventually, the system of quantum vortices inside must reorganize, causing the rotational speeds to suddenly align. When this happens, the fast-spinning liquid transfers its momentum to the already slow-spinning star, and we observe the neutron star abruptly speed up. These events, known as glitches, offer what is likely a unique chance to study fluid dynamics on an immense scale, since we certainly can't build a 10-meter container on Earth and fill it with superfluid neutrons. One phenomenon we haven't touched on yet is precession. If you spin a top so that its axis isn't perfectly vertical, you'll see it not only spin but also wobble, its axis tracing a slow circle. Both the Earth's axis and neutron stars can precess, but there's a complication. A core of superfluid neutron liquid contains vortices, and each vortex behaves like a miniature gyroscope, fiercely resisting any change in its orientation. This very principle is why gyroscopes are used in the guidance systems of rockets and satellites. Precession would try to force these vortices to turn, but they push back, which could mean that the kind of wobble we see in a spinning top might not occur in neutron stars at all. So far, observations haven't provided a definitive answer. After studying a couple of thousand radio pulsars, astronomers have found only a few instances of behavior that could possibly be explained by precession, with a couple more examples in close binary systems. However, there is no widespread evidence for the precessional behavior of superfluid liquids inside these compact objects. Superfluidity can also trigger the transformation of elementary particles, which brings us to a fundamental question. What is a neutron star actually made of? The simple answer is neutrons, but the reality might be entirely different. Imagine you're in a student cafeteria and see a sign for a beef cutlet. In your naivete, you assume it's made of beef. But it's not so straightforward. It might contain some beef or perhaps very little. The situation with a neutron star is quite similar. Indeed, some of the oldest, most conservative models propose that a neutron star is composed of about 80% neutrons. However, it's also plausible that a neutron star contains only 20 or 30% neutrons, with the remainder consisting of some other exotic particles. In this sense, it's very much like that cafeteria cutlet, where the name doesn't necessarily tell you the full story of its ingredients. This phenomenon occurs because the immense gravity of a neutron star compresses matter so intensely that the star effectively crushes itself. The resulting density can surpass that of an atomic nucleus by a factor of 10, unlocking all kinds of extraordinary physics. In our labs, we have no way of replicating such extreme conditions. The closest we can get is by smashing nuclei together in accelerators to create a fleeting, hot, dense medium for study. By contrast, this state of matter exists naturally and permanently within neutron stars. Consequently, the interiors of neutron stars can harbor some truly exotic forms of matter, with quark matter being perhaps the most remarkable example. As you may know, protons and neutrons are not fundamental particles. They are composite, each made of 3 quarks. However, you can't simply isolate a single quark by pulling it out of a proton or neutron. The energy required for such an attempt is so immense that it creates new particles, a quark and an antiquark, leaving the original particle intact and preventing any free quarks from existing. You can, however, approach this from the opposite direction by intensely compressing protons and neutrons together. Under such immense pressure, the quarks, which were previously confined within their individual particles, can break free from their bonds. This process forms what you might call a quark collective, a state known as quark matter. It's a fascinating hypothesis with profound implications, and it seems that the only place in the universe this peculiar substance could exist is deep inside neutron stars. Another point of fascination for physicists involves non-terrestrial electrodynamics, specifically the colossal magnetic fields of neutron stars. These fields are millions of billions of times more powerful than those found on Earth or the Sun, reaching truly staggering magnitudes. Just like the extreme gravity and density, These conditions are impossible for us to replicate in a lab. In such an environment, the familiar laws of electrodynamics behave in very strange ways, leading to all sorts of interesting phenomena that astronomers are now actively working to observe. In physics, it's often the case that a quantity's significance isn't just about being large or small, but about crossing a specific threshold. Magnetic fields have several such critical points, the first of which is a field roughly 1 billion times stronger than the Sun's. At this level, far beyond our laboratory capabilities, an electron's magnetic energy becomes comparable to its Coulomb energy within a hydrogen atom. Once this threshold is surpassed, the atom itself is deformed. Its electron cloud stretches out along the magnetic field lines, transforming the atom into something resembling a cylinder or a needle, which in turn allows for the formation of unique, pseudo-molecular chains. The second critical threshold is known as the Schwinger field, which is tens of times more powerful than the fields found in typical radio pulsars. In such an intense field, an electron's energy from its cyclotron frequency, its circular motion, surpasses its own rest energy. This transition unlocks a range of intriguing effects, most notably that in super-Schwinger fields, a single photon has a high probability of spontaneously creating a particle-antiparticle pair. Under normal circumstances, you need either 2 high-energy gamma rays or 1 extremely energetic one to create an electron-positron pair. But within these powerful magnetic fields, even a relatively low-energy photon can create a pair with a high degree of probability, provided its energy exceeds the combined rest mass of the 2 particles. Furthermore, such an intense field dramatically polarizes the vacuum itself, enabling other quantum electrodynamic processes. An annihilating electron-positron pair can produce just 1 gamma quantum, and photons can even split in 2. The third and final critical value represents the point where the magnetic field becomes so powerful it could physically rupture the neutron star. This theoretical limit is estimated by equating the magnetic field's energy with the star's gravitational binding energy, a value about 1 billion times greater than the Sun's magnetic field. Because this upper limit is so vast, theorists, being a playful group, sometimes model processes using fields just 10 times weaker than this critical value, calculating exotic phenomena that we cannot yet rule out as impossible in nature. Therefore, neutron stars truly serve as unparalleled physics laboratories, where astronomical observations perfectly complement experiments conducted on Earth. If you want to probe the limits of nuclear physics, for instance, building accelerators and reactors isn't enough. You must also deploy satellites to watch neutron stars and monitor intriguing processes like their cooling. It's also worth noting that despite the crushing gravity, these objects possess thin atmospheres that can substantially influence what we observe from afar. A neutron star's atmosphere is defined by its temperature, composition, and the force of its gravity. With some relatively straightforward calculations, you can determine that this atmosphere only extends a few millimeters or centimeters upward, which is neither very far nor particularly dense. However, this thin layer is substantial enough to significantly modify the spectrum of heat radiating from the star's surface. So, you might wonder what this atmosphere is made of. The surface could be composed primarily of iron, which makes sense if you recall that the collapsing core that forms the star is itself iron. Atmospheres made of iron would be the thinnest, because the atoms are so heavy, and their radiation spectrum would generally resemble a thermal, Planckian one, but with many specific spectral features. Unfortunately, actually studying these atmospheres presents a considerable challenge. After an iron core collapses, outer layers containing lighter elements can fall back onto the newly formed star's surface. This means the atmosphere might not just be iron, but could include a mix of everything that was present in the supernova. Furthermore, the heavier elements have a tendency to settle downward due to gravity. Consequently, if a layer of hydrogen ends up on top, the atmosphere you would see as an outside observer would consist mainly of hydrogen, creating the thickest possible atmospheric layer and drastically altering the spectrum in the X-ray range, which is how we typically observe these million-degree surfaces. This variation in composition can easily mislead researchers, as a hydrogen atmosphere can make a neutron star appear hotter than it truly is. There's another possibility as well. Under specific conditions of temperature and composition, the condensate I mentioned earlier can form on the surface. In such a scenario, the neutron star would have a gray appearance, with a spectrum that looks thermal but corresponds to a much lower temperature. If you tried to calculate the star's radius from its luminosity and this incorrect temperature, you would end up with a significant error. Thankfully, scientists have developed methods to correctly identify the atmospheric composition. By carefully analyzing the spectrum of a neutron star, such as the central object in the Cassiopeia A supernova remnant, it was discovered that its atmosphere is predominantly made of carbon. Determining the correct composition is critically important, because failing to account for this thin layer can lead to mistakes in measuring the surface temperature, and by extension, the temperature of the star's interior. A newly formed neutron star is an exceptionally hot object, with an interior temperature that can exceed billions of degrees for a period. For the first 100,000 years of its existence, the star doesn't cool like a typical object, which would radiate heat from its surface. Instead, it cools primarily from its center through the emission of neutrinos. This leads to a fascinating process where heat actually flows inward toward the core, where it effectively vanishes as neutrinos escape freely from the star's interior. Detecting neutrinos directly from a cooling neutron star is an extremely difficult task. For that reason, our main tool for this research is X-ray detectors, since the surface temperature is approximately 1 million degrees. While we don't usually get to watch the gradual cooling of a solitary neutron star in real time, though there might be one case where such data exists, we can often observe this process in binary systems. In these pairs, we can see a neutron star's temperature drop noticeably over a century after a phase of intense accretion comes to an end. By observing many neutron stars at different stages of their lives, we can measure their surface temperatures and piece together the cooling timeline. This gives you new insights into nuclear physics, as the processes of neutrino emission are directly tied to it, allowing astronomical observations to once again enrich laboratory experiments. Observing the neutrino burst from a supernova can also help us understand what kind of compact object was created. Essentially, it tells you whether the outcome was a neutron star or a black hole. If the collapse continues unabated to form a black hole, the neutrino flux will intensify and then suddenly cut off, whereas the birth of a neutron star results in a smoother evolution of the signal. If we had possessed modern neutrino detectors back in 1987, you and I would know precisely what kind of object was formed from the supernova explosion in the Large Magellanic Cloud. Now, I promised we would speculate on what future Nobel Prizes might be awarded for neutron star research. The most probable and immediate candidate is a prize for the direct detection of gravitational waves. We know they exist as a prediction of general relativity, but it's crucial to detect them directly with a laboratory instrument. The most effective way to achieve this is by observing one of nature's most spectacular events, the merger of two neutron stars. To generate a gravitational wave burst powerful enough for our current antennas to potentially detect, you need to start with a massive binary star system. In such a system, the stars explode one by one, each leaving behind a neutron star, and the binary system manages to survive. Over time, these two neutron stars will gradually spiral closer to each other by emitting gravitational waves. The final act of this cosmic dance, the literal collision of one neutron star into another, unleashes a tremendous amount of energy as both gravitational and electromagnetic waves, which should be an incredible event to witness. This is not just a spectacle. It is fundamentally important for physics, which is why several dedicated gravitational wave antennas have been constructed. To give you a sense of its significance, when American scientists were planning their antennas, another major project, the superconducting super collider in Texas, was also being planned to discover the Higgs boson. When scientific budgets had to be cut, it was the super collider project that was cancelled to ensure the gravitational wave observatories were built. It might surprise you to learn that the scientific community effectively prioritized gravitational waves over the Higgs boson. While a collider is far more costly than a gravitational wave antenna, the National Science Foundation's project, with the price tag exceeding $500 million, was nearly cancelled in 1993. This occurred amidst the immense excitement for the superconducting super collider, suggesting that some researchers believe other pursuits are just as fundamental as the Higgs boson itself. In fact, a future Nobel Prize could very well be awarded for uncovering the properties of matter deep inside neutron stars. The question of what constitutes the core of a neutron star remains one of the most significant unsolved problems in all of nuclear physics. To understand this, you can picture a thought experiment where we continuously compress a piece of matter by adding more of it to a neutron star. As you add material, the star grows more massive, increasing the gravitational pressure on its own core and causing the central density to climb. This process cannot continue indefinitely because at a certain point, the density will hit a critical limit where matter can no longer withstand the pull of gravity. At that moment, the neutron star collapses in on itself and forms a black hole. Pinpointing when this collapse occurs, in other words, determining the maximum possible mass for a neutron star, would provide the key to understanding how matter behaves under such extreme densities. So how could we observe this? The ideal scenario would involve watching an X-ray source powered by a neutron star, observing its regular pulsations, and then suddenly seeing it vanish. The source might still emit X-rays from its surrounding accretion disk, but the telltale pulses from the star's rotation would be gone, replaced by a black hole. Catching this exact moment, however, is incredibly improbable. Since direct observation is so unlikely, we can turn to other methods, such as studying the mergers of neutron stars, which can sometimes result in the formation of a black hole. Another promising, though less direct strategy, is to hunt for progressively more massive neutron stars, a task that astronomers working with binary radio pulsars are actively engaged in. Success in this area, however, often comes down to a significant amount of luck. A more dependable path toward understanding the interior of these compact objects involves accurately measuring both the mass and the radius of a neutron star at the same time. To achieve this, specialized space-based projects are currently in development. One new instrument is slated for installation on the International Space Station, while others are being designed as independent satellites, all aimed at finally solving the mystery of what neutron stars are made of. A discovery undoubtedly worthy of a Nobel Prize in physics.